Polyurethane is a polymer composed of a chain of organic units joined by carbamate links. While most polyurethanes are thermosetting polymers that do not melt when heated, thermoplastic polyurethanes are also available. Polyurethane polymers are traditionally and most commonly formed by reacting a di- or polyisocyanate with a polyol. Both the isocyanates and polyols used to make polyurethanes contain on average 2 or more functional groups per molecule. Some noteworthy recent efforts have been dedicated to minimizing the use of isocyanates to synthesize polyurethanes, because the isocyanates raise severe toxicity issues. Non-isocyanate-based polyurethanes have recently been developed as a new class of polyurethane polymers to mitigate health and environmental concerns. Polyurethane products often are simply called a uro or urethane as a uro, but should not be confused with ethyl carbamate, which is also called urethane. Polyurethanes neither contain nor are produced from ethyl carbamate. Polyurethanes are used in the manufacture of flexible, high-resilience foams seating, rigid foam insulation panels, microcellular foam seals and gaskets, durable elastomeric wheels and tires, automotive suspension bushings, electrical potting compounds, high-performance adhesives, surface coatings and surface sealants, synthetic fibers, carpet underlay, hard plastic parts, hoses and skateboard wheels. History: Otto Bayer and his co-workers at IG Farben in Leverkusen, Germany, first made polyurethanes in 1937. The new polymers had some advantages over existing plastics that were made by polymerizing olefins, or by polycondensation, and were not covered by patents obtained by Wallace Carothers on polyesters. Early work focused on the production of fibers and flexible foams, and PUs were applied on a limited scale as aircraft coating during World War II. Polyisocyanates became commercially available in 1952, and production of flexible polyurethane foam began in 1954 using toluene disocyanate and polyester polyols. These materials were also used to produce rigid foams, gum rubber, and elastomers. Linear fibers were produced from hexamethylene disocyanate and 1,4-butanediol. In 1956 DuPont introduced polyether polyols, specifically poly-tetramethylene ether, glycol and BASF, and Dow Chemical started selling polyalkylene glycols in 1957. Polyether polyols were cheaper, easier to handle and more water-resistant than polyester polyols, and became more popular. Union Carbide and Mobe, a U.S. Monsanto-Bayer joint venture, also began making polyurethane chemicals. In 1960 more than 45,000 metric tons of flexible polyurethane foams were produced. The availability of chlorofluoroalkyl blowing agents, inexpensive polyether polyols, and methylene diphenyl disocyanate allowed polyurethane rigid foams to be used as high-performance insulation materials. In 1967, urethane-modified polyisocyanurate rigid foams were introduced, offering even better thermal stability and flammability resistance. During the 1960s, automotive interior safety components such as instrument and door panels were produced by backfilling thermoplastic skins with semi-rigid foam. In 1969, Bayer exhibited an all-plastic car in Darwin-Kürtisseldorf, Germany. Parts of this car, such as the fascia and body panels, were manufactured using a new process called RIM, reaction injection molding, in which the reactants were mixed then injected into a mold. The addition of fillers, such as milled glass, mica, and processed mineral fibers gave rise to reinforced RIM, which provided improvements in flexural modulus, reduction in coefficient of thermal expansion and thermal stability. This technology was used to make the first plastic body automobile in the United States, the Pontiac Fiero, in 1983. Further increases in stiffness were obtained by incorporating pre-placed glass mats into the RIM mold cavity, also known broadly as resin injection molding or structural RIM. Starting in the early 1980s, water-blown microcellular flexible foams were used to mold gaskets for automotive panels and air filter seals, replacing PVC. Plastisol from automotive applications have greatly increased market share. Polyurethane foams are now used in high-temperature oil filter applications. Polyurethane foam is sometimes made using small amounts of blowing agents to give less dense foam, better cushioning, energy absorption or thermal insulation. In the early 1990s, because of their impact on ozone depletion, the Montreal Protocol restricted the use of many chlorine-containing blowing agents, such as trichlorofluoromethane. By the late 1990s, the use of blowing agents such as carbon dioxide, pentane, 1,1,1,2-tetrafluoroethane and 1,1,1,3,3-pentafluoropropane were widely used in North America and the EU, although chlorinated blowing agents remained in use in many developing countries. In the 1990s, new two-component polyurethane and hybrid polyurethane polyurea elastomers were used for spray-in-place load bed liners and military marine applications for the U.S. Navy. A one-part polyurethane is specified as high-durability deck coatings under MIL-PRF 32171 for the U.S. Navy. This technique for coating creates a durable, abrasion-resistant composite with the metal substrate, and eliminates corrosion and brittleness associated with drop-in thermoplastic bed liners. Rising costs of petrochemical feedstocks and an enhanced public desire for environmentally friendly green products raised interest in polyols derived from vegetable oils. One of the most vocal supporters of these polyurethanes made using natural oil polyols is the Ford Motor Company. Chemistry: polyurethanes are in the class of compounds called reaction polymers, which include epoxies, unsaturated polyesters, and phenolics. Polyurethanes are produced by reacting an isocyanate containing two or more isocyanate groups per molecular nP-mol2N, with a polyol containing on average two or more hydroxy groups per molecular nP-mol2N, in the presence of a catalyst. The properties of a polyurethane are greatly influenced by the types of isocyanates and polyols used to make it. Long, flexible segments, contributed by the polyol, give soft, elastic polymer. High amounts of cross-linking give tough or rigid polymers. Long chains and low cross-linking give a polymer that is very stretchy. Short chains with lots of cross-links produce a hard polymer, while long chains and intermediate cross-linking give a polymer useful for making foam. The cross-linking present in polyurethanes means that the polymer consists of a three-dimensional network and molecular weight is very high. In some respects, a piece of polyurethane can be regarded as one giant molecule. One consequence of this is that typical polyurethanes do not soften or melt when they are heated. They are thermosetting polymers. The choices available for the isocyanates and polyols, in addition to other additives and processing conditions, allow polyurethanes to have the very wide range of properties that make them such widely used polymers. Isocyanates are very reactive materials. This makes them useful in making polymers but also requires special care in handling and use. The aromatic isocyanates, diphenylmethane disocyanate or toluene disocyanate, are more reactive than aliphatic isocyanates, such as hexamethylene disocyanate or isophorone disocyanate. Most of the isocyanates are difunctional, that is, they have exactly two isocyanate groups per molecule. An important exception to this is polymeric diphenylmethane disocyanate, which is a mixture of molecules with 2, 3, and 4 or more isocyanate groups. In cases like this, the material has an average functionality greater than 2, commonly 2.7. Polyols are polymers in their own right and have on average 2 or more hydroxyl groups per molecule. Polyether polyols are mostly made by copolymerizing ethylene oxide and propylene oxide with a suitable polyol precursor. Polyester polyols are made similarly to polyester polymers. The polyols used to make polyurethanes are not pure compounds, since they are often mixtures of similar molecules with different molecular weights and mixtures of molecules that contain different numbers of hydroxyl groups, which is why the average functionality is often mentioned. Despite them being complex mixtures, industrial-grade polyols have their composition sufficiently well controlled to produce polyurethanes having consistent properties. As mentioned earlier, it is the length of the polyol chain and the functionality that contribute much to the properties of the final polymer. Polyols used to make rigid polyurethanes have molecular weights in the hundreds, while those used to make flexible polyurethanes have molecular weights up to 10,000 or more. The polymerization reaction makes a polymer containing the urethane linkage, RUNCUR, and is catalyzed by tertiary amines, such as 1,4-diisobisacchalo, 2.2.2, octane, and metallic compounds, such as dibutyltin dilaurate or bismuth octanoate. This is often referred to as the gelation reaction or simply gelling. If water is present in the reaction mixture, the isocyanate reacts with water to form a urea linkage and carbon dioxide gas, and the resulting polymer contains both urethane and urea linkages. This reaction is referred to as the blowing reaction and is catalyzed by tertiary amines like bis, 2-dimethylaminoethyl, ether. A third reaction, particularly important in making insulating rigid foams, is the isocyanate trimerization reaction, which is catalyzed by potassium octoide, for example. One of the most desirable attributes of polyurethanes is their ability to be turned into foam. Making a foam requires the formation of a gas at the same time as the urethane polymerization is occurring. The gas can be carbon dioxide, either generated by reacting isocyanate with water or added as a gas, or produced by boiling volatile liquids. In the latter case, heat generated by the polymerization causes the liquids to vaporize. The liquids can be HFC-245Fa and HFC-134A, and hydrocarbons such as N-pentane. The balance between gelation and blowing is sensitive to operating parameters including the concentrations of water and catalyst. The reaction to generate carbon dioxide involves water reacting with an isocyanate, first forming an unstable carbamic acid, which then decomposes into carbon dioxide and an amine. The amine reacts with more isocyanate to give a substituted urea. Water has a very low molecular weight, so even though the weight percent of water may be small, the molar proportion of water may be high and considerable amounts of urea produced. The urea is not very soluble in the reaction mixture and tends to form separate hard segment phases consisting mostly of pourea. The concentration and organization of these pourea phases can have a significant impact on the properties of the polyurethane foam. High-density microcellular foams can be formed without the addition of blowing agents by mechanically frothing or nucleating the polyol component prior to use. Surfactants are used in polyurethane foams to emulsify the liquid components, regulate cell size, and stabilize the cell structure to prevent collapsing surface defects. Rigid foam surfactants are designed to produce very fine cells and a very high closed cell content. Flexible foam surfactants are designed to stabilize the reaction mass while at the same time maximizing open cell content to prevent the foam from shrinking. An even more rigid foam can be made with the use of specialty trimerization catalysts which create cyclic structures within the foam matrix, giving a harder, more thermally stable structure, designated as polyisocyanourate foams. Such properties are desired in rigid foam products used in the construction sector. Careful control of viscoelastic properties by modifying the catalysts and polyols used can lead to memory foam, which is much softer at skin temperature than at room temperature. Foams can be either closed cell, where most of the original bubbles or cells remain intact, or open cell, where the bubbles have broken but the edges of the bubbles are stiff enough to retain their shape. Open cell foams feel soft and allow air to flow through, so they are comfortable when used in seat cushions or mattresses. Closed-cell rigid foams are used as thermal insulation, for example in refrigerators. Microcellular foams are tough elastomeric materials used in coverings of car steering wheels or shoe soles. Raw materials, the main ingredients to make a polyurethane are isocyanates and polyols. Other materials are added to help processing the polymer or to change the properties of the polymer. Isocyanates. Isocyanates used to make polyurethane must have two or more isocyanate groups on each molecule. The most commonly used isocyanates are the aromatic diisocyanants, toluene disocyanate and methylene divinyl disocyanate, MDI. TDI and MDI are generally less expensive and more reactive than other isocyanates. Industrial-grade TDI and MDI are mixtures of isomers, and MDI often contains polymeric materials. They are used to make flexible foam, rigid foam elastomers, and so on. The isocyanates may be modified by partially reacting them with polyols or introducing some other materials to reduce volatility of the isocyanates, decrease their freezing points to make handling easier or to improve the properties of the final polymers. Aliphatic and cycloaliphatic isocyanates are used in smaller volumes, most often in coatings and other applications where color and transparency are important since polyurethanes made with aromatic isocyanates tend to darken on exposure to light. The most important aliphatic and cycloaliphatic isocyanates are 1,6-hexamethylene disocyanate, 1-isocyanato-3-isocyanatomethyl 3, 5,5-trimethylcyclohexane, and 4,4-diisocyanatodicyclohexylmethane. Polyols can be polyether polyols, which are made by the reaction of epoxides with an active hydrogen-containing starter compounds, or polyester polyols, which are made by the polycondensation of multifunctional carboxylic acids and hydroxyl compounds. They can be further classified according to their end use. Higher molecular weight polyols are used to make more flexible polyurethanes while lower molecular weight polyols make more rigid products. Polyols for flexible applications use low-functionality initiators such as dipropylene glycol, glycerine or a sorbitol water solution. Polyols for rigid applications use high-functionality initiators such as sucrose, sorbitol, toluenediamine, and mannage bases. Propylene oxide and/or ethylene oxide is added to the initiators until the desired molecular weight is achieved. The order of addition and the amounts of each oxide affect many polyol properties, such as compatibility, water solubility, and reactivity. Polyols made with only propylene oxide are terminated with secondary hydroxyl groups and are less reactive than polyols capped with ethylene oxide, which contain a higher percentage of primary hydroxyl groups. Graft polyols contain finely dispersed styrene acrylonitrile, or polyurea polymer solids chemically grafted to a high molecular weight polyether backbone. They are used to increase the load-bearing properties of low-density high-resiliency foam, as well as add toughness to microcellular foams and cast elastomers. Initiators such as ethylenediamine and trithanolamine are used to make low molecular weight rigid foam polyols that have built-in catalytic activity due to the presence of nitrogen atoms in the backbone. A special class of polyether polyols, poly-tetramethylene ether glycols, which are made by polymerizing tetrahydrofuran, are used in high-performance coating, wetting and elastomer applications. Conventional polyester polyols are based on virgin raw materials and are manufactured by the direct polyesterification of high-purity decids and glycols, such as adipic acid and 1,4-butanediol. Polyester polyols are usually more expensive and more viscous than polyether polyols, but they make polyurethanes with better solvent, abrasion, and cut resistance. Other polyester polyols are based on reclaimed raw materials. They are manufactured by transesterification of recycled polyethylene terephthalate, or dimethyl terephthalate distillation bottoms with glycols such as diethylene glycol. These low molecular weight, aromatic polyester polyols are used in rigid foam, and bring low cost and excellent flammability characteristics to polyisocyanurate boardstock and polyurethane spray foam insulation. Specialty polyols include polycarbonate polyols, polycarprolactone polyols, polybutadiene polyols, and polysulfide polyols. The materials are used in elastomer, sealant, and adhesive applications that require superior weatherability and resistance to chemical and environmental attack. Natural oil polyols derived from castor oil and other vegetable oils are used to make elastomers, flexible bundstock, and flexible molded foam. Copolymerizing chlorotetrafluoroethylene or tetrafluoroethylene with vinyl ethers containing hydroxyalkyl vinyl ether produces fluorinated polyols. Two-component fluorinated polyurethane prepared by reacting FeVe fluorinated polyols with polyisocyanate have been applied for make ambient cure paint coating. Since fluorinated polyurethanes contain high percentage of fluorine carbon bond which is the strongest bond among all chemical bonds. Fluorinated polyurethanes have excellent resistance to UV, acids, alkali, salts, chemicals, solvents, weathering, corrosion, fungi and microbial attack. These have become the first choice for high-performance coating paints. Chain extenders and crosslinkers. Chain extenders and crosslinkers are low molecular weight hydroxyl and terminated compounds that play an important role in the polymer morphology of polyurethane fibers, elastomers, adhesives, and certain integral skin and microcellular foams. The elastomeric properties of these materials are derived from the phase separation of the hard and soft copolymer segments of the polymer, such that the urethane hard segment domains serve as crosslinks between the amorphous polyether soft segment domains. This phase separation occurs because the mainly non-polar, low-melting soft segments are incompatible with the polar, high-melting hard segments. The soft segments, which are formed from high molecular weight polyols, are mobile and are normally present in coiled formation, while the hard segments, which are formed from the isocyanate and chain extenders, are stiff and immobile. Because the hard segments are covalently coupled to the soft segments, they inhibit plastic flow of the polymer chains, thus creating elastomeric resiliency. Upon mechanical deformation, a portion of the soft segments are stressed by uncoiling, and the hard segments become aligned in the stress direction. This reorientation of the hard segments and consequent powerful hydrogen bonding contributes to high tensile strength, elongation, and tear resistance values. The choice of chain extender also determines flexural, heat, and chemical resistance properties. The most important chain extenders are ethylene glycol, 1,4-butanediol, 1,6-hexanediol, cyclohexandimethanol and hydroquinone bis, 2-hydroxyethyl, ether. All of these glycols form polyurethanes that phase separate well and form well-defined hard segment domains, and are melt-processable. They are all suitable for thermoplastic polyurethanes with the exception of ethylene glycol, since its derived bisphenol urethane undergoes unfavorable degradation at high hard segment levels. Diethanolamine and trithanolamine are used in flex-molded foams to build firmness and add catalytic activity. Diethyltoluenediamine is used extensively in RIM, and in polyurethane and polyurea elastomer formulations. Catalysts. Polyurethane catalysts can be classified into two broad categories, compounds and metal complexes. Traditional catalysts have been tertiary amines such as triethylenediamine, dimethylcyclohexylamine, and dimethylethanolamine. Tertiary catalysts are selected based on whether they drive the urethane reaction, the urea reaction, or the isocyanate trimerization reaction. Catalysts that contain a hydroxyl group or secondary amine, which react into the polymer matrix, can replace traditional catalysts, thereby reducing the amount of them that can come out of the polymer. Metallic compounds based on mercury, lead, tin, bismuth, and zinc are used as polyurethane catalysts. Mercury carboxylates are particularly effective catalysts for polyurethane elastomer, coating and sealant applications, since they are very highly selective towards the polyol plus isocyanate reaction, but they are toxic. Bismuth and zinc carboxylates have been used as alternatives. Alkyl tin carboxylates, oxides and mercaptides oxides are used in all types of polyurethane applications. Tin mercaptides are used in formulations that contain water, as tin carboxylates are susceptible to hydrolyses. Surfactants. Surfactants are used to modify the characteristics of both foam and non-foam polyurethane polymers. They take the form of polydimethylsiloxane polyoxyalkylene block copolymers, silicone oils, non-alphenyl ethoxylates, and other organic compounds. In foams, they are used to emulsify the liquid components, regulate cell size, and stabilize the cell structure to prevent collapse and subsurface voids. In non-foam applications they are used as air release and anti-foaming agents, as wetting agents, and are used to eliminate surface defects such as pinholes, orange peel, and sink marks. Production. Polyurethanes are produced by mixing two or more liquid streams. The polyol stream contains catalysts, surfactants, blowing agents and so on. The two components are referred to as a polyurethane system, or simply a system. The isocyanate is commonly referred to in North America as the A side or just the ISO. The blend of polyols and other additives is commonly referred to as the B-side or as the poly. This mixture might also be called a resin or resin blend. In Europe the meanings for A-side and B-side are reversed. Resin blend additives may include chain extenders, cross-linkers, surfactants, flame retardants, blowing agents, pigments, and fillers. Polyurethane can be made in a variety of densities and hardnesses by varying the isocyanate, polyol or additives. Health and safety. Fully reacted polyurethane polymer is chemically inert. No exposure limits have been established in the U.S. by OSHA or ACGIH. It is not regulated by OSHA for carcinogenicity. Polyurethane polymer is a combustible solid and can be ignited if exposed to an open flame. Decomposition from fire can produce mainly carbon monoxide, and trace nitrogen oxides and hydrogen cyanide. Liquid resin blends and isocyanates may contain hazardous or regulated components. Isocyanates are known skin and respiratory sensitizers. Additionally, amines, glycols, and phosphate present in spray polyurethane foams present risks. In the United States, additional health and safety information can be found through organizations such as the Polyurethane Manufacturers Association and the Center for the Polyurethanes Industry, as well as from polyurethane system and raw material manufacturers. Regulatory information can be found in the Code of Federal Regulations Title 21 and Title 40. In Europe, health and safety information is available from ISOPA, the European Dissocyanate and Polyol Producers Association. Manufacturing. The methods of manufacturing polyurethane finished goods range from small, hand-pour piece part operations to large, high-volume bunstock and boardstock production lines. Regardless of the end product, the manufacturing principle is the same: to meter the liquid isocyanate and resin blend at a specified stoichiometric ratio, mix them together until a homogeneous blend is obtained, dispense the reacting liquid into a mold or onto a surface, wait until it cures, then demold the finished part. Dispensing equipment. Although the capital outlay can be high, it is desirable to use a meter mix or dispense unit for even low-volume production operations that require a steady output of finished parts. Dispense equipment consists of material holding tanks, metering pumps, a mix head, and a control unit. Often, a conditioning or heater-chiller unit is added to control material temperature in order to improve mix efficiency, cure rate, and to reduce process variability. Choice of dispense equipment components depends on shot size, throughput, material characteristics such as viscosity and filler content, and process control. Material day tanks may be single to hundreds of gallons in size, and may be supplied directly from drums, IBCs, or bulk storage tanks. They may incorporate level sensors, conditioning jackets, and mixers. Pumps can be sized to meter in single grams per second up to hundreds of pounds per minute. They can be rotary, gear, or piston pumps, or can be specially hardened lance pumps to meter liquids containing highly abrasive fillers such as wollastonite, chopped or hammer-milled glass fibers. The pumps can drive low-pressure or high-pressure dispense systems. Mix heads can be simple static mix tubes, rotary element mixers, low-pressure dynamic mixers, or high-pressure hydraulically actuated direct impingement mixers. Control units may have basic on-off or Euro dispense stop switches, and analog pressure and temperature gauges, or may be computer-controlled with flow meters to electronically calibrate mix ratio, digital temperature and level sensors, and a full suite of statistical process control software. Add-ons to dispense equipment include nucleation or gas injection units, and third or fourth stream capability for adding pigments or metering in supplemental additive packages. Tooling, distinct from pour-in-place, bun and boardstock, and coating applications, the production of piece parts requires tooling to contain and form the reacting liquid. The choice of mold-making material is dependent on the expected number of uses to end of life, molding pressure, flexibility, and heat transfer characteristics. RTV silicone is used for tooling that has an EOL in the thousands of parts. It is typically used for molding rigid foam parts, where the ability to stretch and peel the mold around undercuts is needed. The heat transfer characteristic of RTV silicone tooling is poor. High-performance, flexible polyurethane elastomers are also used in this way. Epoxy, metal-filled epoxy, and metal-coated epoxy is used for tooling that has an EOL in the tens of thousands of parts. It is typically used for molding flexible foam cushions and seating, integral skin and microcellular foam padding, and shallow draft RIM bezels and fascia. The heat transfer characteristic of epoxy tooling is fair. The heat transfer characteristic of metal-filled and metal-coated epoxy is good. Copper tubing can be incorporated into the body of the tool, allowing hot water to circulate and heat the mold surface. Aluminum is used for tooling that has an EOL in the hundreds of thousands of parts. It is typically used for molding microcellular foam gasketing and cast elastomer parts, and is milled or extruded into shape. Mirror finish stainless steel is used for tooling that imparts a glossy appearance to the finished part. The heat transfer characteristic of metal tooling is excellent. Finally, molded or milled polypropylene is used to create low-volume tooling for molded gasket applications. Instead of many expensive metal molds, low-cost plastic tooling can be formed from a single metal master, which also allows greater design flexibility. The heat transfer characteristic of polypropylene tooling is poor, which must be taken into consideration during the formulation process. Applications. In 2007, the global consumption of polyurethane raw materials was above 12 million metric tons, the average annual growth rate is about 5%. Revenues generated with PUR on the global market are expected to rise to approximately $80 billion by 2020. Effects of visible light. Polyurethanes, especially those made using aromatic isocyanates, contain chromophores which interact with light. This is of particular interest in the area of polyurethane coatings, where light stability is a critical factor and is the main reason that aliphatic isocyanates are used in making polyurethane coatings. When PU foam, which is made using aromatic isocyanates, is exposed to visible light it discolors, turning from off-white to yellow to reddish-brown. It has been generally accepted that apart from yellowing, visible light has little effect on foam properties. This is especially the case if the yellowing happens on the outer portions of a large foam, as the deterioration of properties in the outer portion has little effect on the overall bulk properties of the foam itself. It has been reported that exposure to visible light can affect the variability of some physical property test results. Higher energy UV radiation promotes chemical reactions in foam, some of which are detrimental to the foam structure. Degradation. When chlorine gas reacts with water, HCl and HOCl form and HCl causes the decomposition of the inner part of the polyurethane tubing into Ns salts and the polyol. Two species of the Ecuadorian fungus Pestalozchiopsis are capable of biodegrading polyurethane in aerobic and anaerobic conditions such as found at the bottom of landfills. Degradation of polyurethane items at museums has been reported by many researchers. Polyester-type polyurethanes are more easily biodegraded by fungus than polyether type. See also, thermoplastic polyurethanes, passive fire protection, penetrant, references. External links, Center for the Polyurethanes Industry, information for EH&S issues related to polyurethanes developments, polyurethane synthesis, Polymer Science Learning Center, University of Southern Mississippi, Polyurethane Foam Association, Industry Information, Educational Materials and Resources related to Flexible Polyurethane Foam, PU Europe, European PU Insulation Industry Association, European Voice for the National Trade Associations representing the polyurethane insulation industry. ISOPA, European Dissocyanate and Polyol Producers Association, ISOPA represents the manufacturers in Europe of aromatic disocyanates and polyols.